Imagine a world bathed in vast amounts of invisible matter. A world where there are more things hidden in the shadows and darkness around you than all the things you can actually see. Well, you are already living in that world. And to understand why, I need to tell you about dark matter, which was given that name. After all, the unknown must be given a name. A type of matter that no one has ever directly seen and whose nature remains completely unknown, but whose mass still accounts for more than 80% of all the matter in the universe. We actually think that there exists, alongside the ordinary form of matter that makes up everything we know, you and me, the stars, the galaxies, another form of matter spread out everywhere, all around us, and 5 times more abundant than the ordinary matter we're familiar with. In short, as you can see, today we're going to dive into one of the greatest mysteries of modern science, the mystery of the missing universe, the dark side of matter. But before we take a closer look at the nature of this strange substance, we'll need to look back at the history of its discovery and the clues in space that led us to it. The first time people began to suspect the existence of a large amount of invisible matter was in the 1930s. When studying a vast cluster of hundreds of galaxies, it was observed that these galaxies were rotating abnormally fast around the center of gravity of their cluster. However, with such incredible speeds, the galaxies should have been expelled from the cluster a long time ago, because their combined mass is far from sufficient to allow them to remain gravitationally bound to each other. So there had to be something extremely massive there, which, by significantly increasing the strength of the gravitational field within the cluster, prevents it from breaking apart, allows it to remain coherent thanks to this matter, which we cannot see. By looking at the data, we were able to estimate its significance on the scale, and the result is clear. We're not talking about a small problem here, because to counterbalance the crazy speeds of the galaxies and thus prevent the system from dispersing, it was estimated that there must be about 100 times more hidden matter in this cluster than the amount we can observe. Strangely, at the time, this astonishing discovery didn't make much noise. Until, about 40 years later, it was brought out of the closet again. Because, in the 1970s, by studying in detail the rotation speeds of stars around the centers of spiral galaxies like ours, the Milky Way, or Andromeda, something terribly troubling was discovered. The rotation speeds of stars at the outskirts of these galaxies are abnormally high, so much so that, once again, a large part of them should have been, as if by a slingshot effect, torn away from their galaxies and sent drifting into the cosmos. To understand why these observations are strange, let's take the example of our solar system. Within it, almost all of the mass is located at the center, in the star and around it. The planets orbit more and more slowly as you move farther away. Thus, while the Earth speeds around the Sun at nearly 30 kilometers, Pluto, which is about 40 times farther away, orbits at only about 5 kilometers. Since the laws of celestial mechanics are what they are, as a first approximation, should the rotational speeds of stars around the galactic center also decrease as you move farther away? Because it is in the central region that the vast majority of matter, and therefore mass, is concentrated in the form of stars, clouds, gas, and dust. And there are even supermassive black holes there. However, the rotational speeds of stars in the spiral arms do not decrease as the distance from the center increases. Once again, the presence of only the observed ordinary matter does not explain this oddity. It's as if there is also a powerful and invisible connection here. Another source of mass, allowing galaxies to remain stable and coherent to keep their peripheral stars over time. And it is by carefully processing the data accumulated from these kinds of observations that we have come to estimate that this hidden, staggering mass accounts for more than 80% of all the matter in the universe. At first, faced with the evidence that there is something whose combined mass really tips the scales, at first we imagined this matter was made up of the same elements as everything around us, that is, protons, neutrons, and electrons. In short, just ordinary matter that, in space, would have accumulated in large quantities in celestial bodies that slipped under the radar and are almost impossible to see. Celestial bodies that emit or reflect extremely little light, such as brown dwarfs, remnants of failed or cooled stars, neutron stars, or drifting black holes. The problem is that if this kind of ordinary but incredibly dark matter really accounts for 80% of the matter present in the universe, then the celestial bodies hosting it should exist in very, very large quantities in galaxies like ours, to the point that these dark bodies should have already been detected. because when passing in front of distant stars, they should disturb the light coming to us from them. Yet, to this day, and despite intense search campaigns, nothing like that has ever been observed. And as it stands, with the possible exception of primordial black holes, very particular black holes that would have formed during the very first moments of the universe, and that would be so small in size that they would become extremely difficult to detect. The latest observations all seem to invalidate the hypothesis that this unknown mass comes from ordinary matter that is simply impossible to see. In any case, this hypothesis struggles to pass the test of quantities, because at most, it can only explain 20% of the amount of missing mass. That's why, for quite some time now, we've been leaning toward a much more unsettling explanation, the one we mentioned in the introduction. A most bizarre dark matter, an absolutely unknown substance made up of exotic subatomic particles, with the strange characteristic of not clumping together like ordinary matter does. And to really understand its astonishing nature, we'll have to look at how it's distributed around us. In other words, where is it? Here is an artist's view of our galaxy, where you can see almost all of the ordinary matter spread out in a plane, concentrated in the form of stars and clouds, gas and dust. But if you could, as if by a miracle, observe both ordinary and dark matter at the same time, then the appearance of this galaxy would be transformed, because dark matter would extend far beyond what is possible to see, taking the form of immense, extraordinarily diffuse bubbles. It is believed that this halo is 5 times heavier and nearly 10 times more extensive than the entire visible part that surrounds it. That's because the particles of dark matter that make up this diffuse fog are unable to clump together, to stick to each other to form coherent and solid objects like the matter that surrounds us does. Because, unlike ordinary matter particles, which can lose energy by radiating and thus slow down, condense, and pile up, to give birth to simple dust, asteroids, or through gravitational collapse, to stars and planets, are dark matter particles unable to clump together, and our entire galaxy is therefore most likely immersed in a soup of exotic, extremely diluted particles. Which means that right now, there are billions of completely unknown particles permeating all of space. But before we go into more detail about the nature of these elusive ghosts, let's take a moment to look at the indirect evidence of their presence on the large scales of the cosmos, where the hunt for shadows often proves to be fruitful. Because something with such colossal mass leaves traces of its presence in the sky by interacting with the universe of ordinary matter that we know, and this happens through the faint force of gravity. As shown by this striking image, where we can see other groups of galaxies that have collided with each other, and where most of the mass is not, contrary to what one might think, at the center of the image. That's where the ordinary matter gas from the 2 clusters has heated up and slowed down, leaving behind a shock wave shown in pink. In fact, here, most of the matter is found on either side of the collision region, as if, when the 2 groups collided, and while much of the intergalactic gas made of ordinary matter slowed down to concentrate, the dark matter surrounding the 2 clusters ghostly passed through the clouds of ordinary matter gas and dust. In these titanic collisions, dark matter reveals itself through the influence it exerts on ordinary matter, but also on the behavior of light, because the presence of large amounts of this mysterious substance can, due to its massive weight, bend the light rays passing through the regions it dominates, and thus create phenomena known as gravitational lensing. These kinds of cosmic mirages occur when large amounts of matter, due to their mass, create them, like bending the fabric of space-time, and thus distorting the light rays reaching us from distant galaxies located in the background. Thus, indirectly, through gravity, which, like a puppeteer, pulls and stretches the strings of the fabric of space-time. These lenses give us an idea of the hidden distribution of this mysterious dark matter on large scales. Except that, as brilliant as this intermediary is, it tells us absolutely nothing about its true nature. So, do we know what these dark matter particles are made of? Do we even have an idea of what this strange matter is composed of? Well, that's where it gets complicated. Because, despite the accumulation of indirect evidence in the macrocosm, diffuse dark matter still eludes us in the microcosm, where researchers are trying to track down neutral, massive, stable, slow, and cold particles, but also ones that are practically insensitive to the electromagnetic force and therefore transparent, neither absorbing nor reflecting light. In short, they're incredibly elusive. The problem is that no known particle has such properties. That's why most people working on the subject think that such particles exist all around us, others than those already listed and which exist in a world of unknown darkness. These hypothetical elementary particles are, at least on paper, numerous and each more fascinating than the last. Some, such as the heavy and supersymmetric neutralinos, would exist in a way on a different level of reality from the others. Others, such as the intriguing multidimensional particles, would be nestled and hidden in extra dimensions and would therefore have more planes of existence than the universe we experience. In short, I'm not going to list the mind-blowing bestiary of all those that theoretical physicists imagine could make up dark matter, and whose names, such as action, technibarium, wimpsia, Gutsia, and other quark nuggets, sound to me like delicious candies. The thing to remember here is that despite decades of research, all the increasingly ingenious experiments set up to try to detect, among the billions of dark matter particles passing through every square meter of our planet every second, those that might deign to interact with the nucleus of ordinary matter have come up empty-handed in the realm of the infinitely small. Dark matter still refuses to come out of the shadows. So, of course, when you think about the fact that these particles are so discrete, that they must be able to pass through a wall of lead several thousand kilometers thick without encountering the slightest resistance, you realize that this lack of detection doesn't necessarily mean that dark matter doesn't exist. Maybe even the level of interaction that is possible at the scale of the infinitely small between dark matter and ordinary matter is too subtle for us to ever detect. And so, forever inaccessible, unless it's just a matter of time and technology. When you think about it, neutrinos, whose existence was postulated in 1930, were only discovered experimentally in 1956. As for the Higgs boson, 48 years separate its theoretical proposal on paper from its discovery in reality. In any case, one thing is certain. There is something out there in the cosmos that resists understanding, to the point that some scientists have come up with other approaches to the problem, suggesting that these mysterious behaviors on large scales could be explained by assuming that dark matter doesn't exist, and that these abnormal movements we observe simply show that our understanding of gravity might be wrong. In other words, the supporters of this hypothesis suggest slightly modifying the laws of gravity to account for the strange behavior of stars and galaxies. On galactic scales, where celestial bodies move in very stable gravitational fields, this approach, known as modified Newtonian dynamics, has actually had some real success in describing the rotation of galaxies. And unfortunately, it struggles to explain the dynamics of clusters, as well as the recent discovery of Dragonfly 44. A galaxy with a mass comparable to that of our Milky Way, but which appears to be made up of more than 99% dark matter. Or conversely, what about this other galaxy, which would be nearly empty of it? Most importantly, the modified Newtonian dynamics theory cannot adequately explain the strength of gravitational lensing phenomena. Like explaining how the universe became what it is today without assuming dark matter was present from the start. Maybe that's the most troubling part of this story. Because without the presence of something lurking in the darkness, the current structure of the universe probably wouldn't exist, and neither you nor I would be here. I think I'm going to have to explain myself, starting from the most fascinating image we've ever obtained of the universe. Here is the cosmic microwave background, a kind of tired light, which, in the microwave range, bathes the entire sky. And in a way, it lets us see the precise moment when the universe went from opaque to transparent. Because this light, which we detect no matter which direction in the sky we look, was emitted 380,000 years after the Big Bang. At the precise moment when matter in the universe became diluted enough for light to finally start traveling through it. Within this fossil radiation, we observe very slight temperature fluctuations, represented here as colored spots. These irregularities allow us to get an idea of the distribution of matter in the primordial universe, because they are due to slight variations in density from one region to another. And then, what this image tells us is that here too are hidden and revealed other bundles of evidence for the existence of this strange dark substance. Because if the universe had contained only the ordinary matter we know in those ancient times, then the temperature disparities in the cosmic microwave background would have been different from what we observe. Indeed, It is believed that the mass of ordinary matter alone cannot explain how these regions of different density could have formed in such short periods of time in terms of cosmic timescales. And to explain their existence, we need, from the very first moments of the universe, the presence of an additional kind of matter, a matter 5 times more abundant in mass than all the known matter in the universe. You'll notice we find the same proportions needed to explain both the unusual speeds of stars in galaxies and of galaxies in clusters. But through a different line of reasoning, we now believe that shortly after the Big Bang, this abundant dark matter, with its strange property of being insensitive to light, began to slowly contract well before ordinary matter did. Thus giving rise, first, to these very slight density fluctuations, which would then have acted like gravitational wells, a kind of immense islands, clumps from which ordinary matter would gather, and the universe would gradually take on its structure. A cosmic tapestry in the shape of a spiderweb, crisscrossed with lines of higher density and dark regions as we know it today. Thus, it is believed that without the initial presence of dark matter, the very history of the universe would have been radically different. As numerical simulations tend to prove, by running time forward in a universe initially rich in dark matter, they end up with structures that are very similar to those observed today. Namely, immense cosmic webs made up of ordinary matter, such as galaxies, shown here in white, which cluster and clump together inside vast halos and diffuse filaments of dark matter, shown here in purple. These regions, where dark matter predominates, form in a way the backbone, the invisible scaffolding, binding together by gravity the great skeleton of the cosmos. In short, as things stand, the dark matter hypothesis is the only one that solves the mystery of this missing mass, which dictates the rhythm of the dance for galaxies as well as for peripheral stars. And even today, the mystery remains opaque as its inner structure continues to elude us. Black remains, for now, the shade of absence. In any case, and whatever its true nature may be, by making us see all sorts of things, dark matter forces us to think outside the frame of the picture. And maybe one day, by chasing its shadows long enough, we will finally uncover the secret of this dark matter, so that in the end, we can see more clearly by turning the light back on. And I don't know about you, but I think that's absolutely amazing. That the vast majority of the matter in the universe is probably made up of something absolutely crazy, different from anything we know. That there is, in the cosmos, 5 times more dark matter of a completely unknown nature than ordinary matter. And that, among these, barely a tenth is visible as gas and stars, while the remaining 90% is made up of a dark form. A matter made of the same elements as those around us, but 10 times more abundant than the stars. And above all, so diluted in the space between galaxies, or concentrated in cold and discrete bodies, such as failed stars or black holes, that it is extremely difficult to observe directly in the visible spectrum with our telescopes. Definitely, the universe contains more than what it shows us.